vectors as what? Containers, right? Or tuples, right? So our examples also are first, we think of vectors as what? Arrays or containers, right? So recall, we saw what a field was, right? Things that you can add, scale, divide. So we define n tuples. So we call this a set of what? N tuples. So n tuples. To be, you have an array with entries all coming from your field. Now, to define a vector space, all you need to do is define what the addition and scalar multiplication is. So how do we add two arrays? We add them entry-wise. So first entry plus second entry here, second entry plus second entry here, and the last entry plus the last entry. Now, how do we scale the vectors? A scalar times a vector, we want the scalar to multiply each of the entries here. Okay, so let me add here. A vector space is defined by the addition and scalar multiplication. Okay. By the addition and scalar multiplication. So given a set, you want to show that with the vector space, all you need to do is to define what addition is and what scalar multiplication is. Good. So we think of vectors as what? Containers or arrays, which is how most of us think about vectors, right? But vectors go beyond arrays, right? They could be matrices, right? You can think of vectors with what? With different attributes. So here we are looking at what? Matrices. So we let the sets max. So here, 2 here represents the number of rows we are considering, and this other 2 here represents the number of columns we are representing, right? So we define this to be what? Entries coming from your field, and define addition and scalar multiplication to be, now, if you have one array and another array, you add them what? Entry-wise. So this entry here is in the first row, first column. So you add it to the entry in the first row, first column. That gives you this. First row, second column, first row, second column. That gives you the addition. What about scalar multiplication? Scalar multiplication is defined by you multiplying each entry in your array by it. You can check that this satisfies all the 10 adjoints of the vector space. But so that means what? Matrices are vectors. So maybe I add a note. So matrices are vectors. Okay. So vectors are not just the tuple that we learned about, right? Even in our next example, we see that vectors can even be continuous functions, right? So if you have a function from a real value function from R to R, which is continuous, then we take the set of all continuous functions from R and define addition of two continuous functions to be what? Individual additions and adding, and scalar multiplication to be this. So lambda f x is just lambda f of x. Then we can show that this is actually a vector space. Okay, so here we see that what? Vectors are not just tuples, right? So we see that here continuous functions, continuous real valued functions are vectors. Okay, so vectors are not just arrays, they are broader than that. Let's see one more example of vectors. Now, if you consider polynomials of any degree, what do we mean by a polynomial? So we are still considering K to be a field, and you define a set where you are finding, you pick a scalar plus a scalar times the variable x plus a scalar times x squared, quadratic, cubic, you go on and on to n power. For any natural, not any natural number, not just any natural, for any non-negative integer with your coefficient coming from the field. Then if you take collection, so this means polynomials of any degree. So you could have degree 0 polynomials, that would be the field. Degree 1 would be linear, degree 2 would be quadratic, cubic, and so on. So that's a very big set. And you define addition. So we need to define a vector space. All we need is what? How is addition defined? We define addition of two polynomials to be this. Degree 0, so as a subscript, degree zeros add, degree 1 elements add, and so on up to degree n elements. And for scalar multiplication, the scalar multiplies each of the coefficients of your variables there. So that means that what polynomials are vectors. So note polynomials are vectors. Polynomials are vectors.